Okay, good morning to all of you. I welcomes to all in our lecture series on classical mechanics, that is your core paper 2 belongs to first semester BSc syllabus. In our last class we have been discussed about two body problem and its reduction to one body problem. In detail we have been discussed. So and today in today class we are going to discuss the energy equation and energy diagram. So I suggest that before you have to watch this video, you go through this topic, last video. Okay, in detail we have been discussed in our last class. So today we have to discuss energy equation of central force motion and energy diagram. Okay, so let's start. The equation of motion under central force using the concept of reduced mass is given by mu r double dot equal to fr r cap. Okay, this is simple equation, that is your Newtonian formula, that is ma equal to f. That's it, according to Newton's second law. This is the equation of motion, that is your m, mass of the body, acceleration is nothing but is your force. So here you can see that mu is the reduced mass. Suppose we have somewhere we have two masses. The reduced mass is mu. So instead of mass m can be written as mu, and we know that r double dot is nothing but acceleration. Okay, r is your position vector. dr by dt is nothing but r dot belongs to velocity. Again, dv by dt will be written as d square r by dt square, or the so-called r double dot, whatever written here, equal to force. This force is nothing but your central force. So you know that central force can be represented in this way. This is your equation number 1. Okay, now here also I written mu is the your reduced mass, fr magnitude of central force. Okay, here we have introduced the plane polar coordinates, that is your r and theta, in the plane of the motion. We know that acceleration of the particle has two components, that is your ar, the radial acceleration is given by this one, and the transverse acceleration a theta is given by this one. So where you got these two expressions, you just check your note. May in your mathematical physics, you have been studied in a first semester, mathematical physics, you can found that orthogonal collinear coordinate system is there. So okay, so in that topic, acceleration in spherical polar coordinate, velocity in spherical polar coordinate, acceleration in cylindrical coordinate, velocity in cylindrical coordinate was inside the syllabus. Okay, you just check your note, mathematical physics note. There you can found, I will show you. Wait 1 second. Here I am telling about orthogonal coordinate system. In this topic you can found the divergence, gradient, curl in the orthogonal coordinate system, which is your generalized coordinate system. From that orthogonal coordinate system you can found other coordinate system, or you can derive other coordinate systems information, uh, uh, may, that may be Cartesian, polar, or cylindrical. Okay, and also in this topic you are going to find out what will be the in general representation of the your what your gradient. Your gradient will be in which way it has to represent, and what will the divergence will be this one the divergence in general. Curl, what will the curl, this one, and what will the Laplace, that means del square, if we are going to consider, then this is the required general expression if we are going to consider orthogonal collinear coordinates. And from that expressions we can derive for Cartesian coordinate systems, gradient, divergence, curl and Laplacian, cylindrical coordinates, gradient, divergence, curl and Laplacian, and spherical polar coordinates. These are inside your course, and you can found that velocity and acceleration in cylindrical coordinate, velocity and acceleration in spherical polar coordinate system. Here in this section you can found that is your acceleration is this one, r double dot minus r theta dot plus phi dot square r sine square theta e r cap, and r double dot 2 r dot theta dot minus r sine theta cos theta phi dot square e theta cap, and r sine theta phi double dot plus 2 r dot phi dot sine theta plus 2 r cos theta dot phi dot e phi cap. This is your acceleration expression in your spherical polar coordinate system, and this is your velocity expression. Velocity expression, that is your r dot e r cap plus r theta dot e theta cap plus r sine theta phi dot e phi cap. I am going to be zoom, you can write it. Okay, this is the expression of the velocity of the particle in spherical polar coordinate, this one, and this is your expression of acceleration when the particle is moving in spherical polar coordinate system. Okay, this is the, now we know that the central force is confined in a plane, that means it has to be contained two coordinate only. So now we are going to consider the central force contains only these two coordinates, radial and theta, and phi is not to be considered. Okay, if it is so, if it is so, then our see phi component not to be accepted, as central force is only confined in two planes. So what component we accepted? This one and this one. Okay, this component, this component. So here we introduce theta r and theta. R theta component we are going to consider. Acceleration of the particle has two components. AR, the radial acceleration. The radial acceleration will be r double dot minus r theta dot square. And as we are not considering phi component, so this will be 0. See, this term contains phi. So as we are not considering phi component, also this term will be 0. The radial component of acceleration we found r double dot minus r theta dot square. R double dot minus r theta dot square r cap. That means along radial, e r cap also represents the radial component. Next, and transverse acceleration or along theta component will be how much? It will be this one, r theta double dot plus 2r dot theta dot, 2r dot theta dot. Okay, this is belongs to theta component. As this term contains phi, so not to be considered, and this component itself, the phi component, the whole component is not going to be considered. So we found that the two components AR, the radial acceleration is given by this one, transverse acceleration A theta is given by this one, right? Now the polar form of equation number 1, the polar form of equation number 1 will be how much? See here, the acceleration may be two components, but the force has only one component, right? This force has only radial component. So we are going to be equivalent radial component of acceleration with the radial component of force, radial component of acceleration, transverse component of acceleration with the transverse component of force. Transverse component of force is how much? 0. So hence equation number 2 will be mu. Here FR r cap means we are going to consider radial component of the acceleration, that will be the r double dot minus r theta dot square radial component is equal to FR r cap. So these two directions cancelled. We found that mu, considering only magnitude of left and right, it will be this one equal to r double dot minus r theta dot square equal to fr. Let it is your equation number 2. Now considering the theta component and equating with right hand side of the component of the force, there is no component we can found the force will be in the transverse direction. So hence mu r theta double dot plus 2r dot theta dot 2r dot theta dot will be equal to 0. Let it is your equation number 3. The equation number 3 value is 0. Why? Because central force is the function of r only and independent of theta. Clear? Now come to the next page. Then the angular momentum of particle remain conserved, we know, in our central force motion. So L equal to mu r square omega is constant. L equal to r into v, right? Sorry, r cross p like that. So it will be r into m into v in circular motion. It will be angular motion. Angular motion v will be r omega. So r square m omega. Here instead of m we have to consider mu. Got it? In case of your angular motion, angular momentum is nothing but r into m into v. That is your, this is your linear momentum. So L equal to r into m into v will be written as r into omega. This is your angular velocity, omega. So L will be equal to r square m omega, or instead of m we can write here mu. R square omega is your angular momentum. So here omega is nothing but your angular velocity, that means d theta by dt. So L can be written as mu r square theta dot. Okay, so here L will be equal to mu r square omega, which is constant. That implies L equal to mu r square theta dot will be constant. Let it is your equation number 4. This is known as the first integral of the motion. See, wherever you are going to be found this word first integral, solution. So here the integral represents that equation from which we can found the solution of that motion. Means we can found the information regarding the dynamics of the motion. Okay, so this is our first expression or first integral from which we can get the information regarding the dynamics. Okay, now from equation number 2, what we are going to get? Equation number 2 is your mu r double dot minus mu r theta dot square is equal to fr, right? So from equation number 2 we can write mu r double dot minus mu r theta dot square equal to fr. So here mu r double dot minus mu r, here theta dot will be nothing but L by mu r square. Theta dot will be L by mu r square. So you just put theta dot value over here. It will be L by mu r square whole square equal to fr, because from equation number 4 theta dot is nothing but L by mu square, right? So now it will be mu r double dot minus L square by mu rq equal to fr. Let it is equation number 5. Now, but the central force is conservative, can be expressed in the term of potential energy as Fr equal to that will be, we know that, minus dv by dr. If a force is conservative, can be represented by the negative gradient of the potential energy. So already we have been studied in our initial classes of this unit. Okay, you can check your note. So now equation number 5 will be mu r double dot minus L square by mu rq minus equal to minus du by dr. So that implies mu r double dot equal to minus del u by del r. This term taken to right hand side, it will be L square by plus L square by mu rq. So collectively I have written that minus del by del r u plus L square by 2 mu r square. You just take the derivative. The first term will be minus du by dr. The second term derivative, if you are going to take, then it will be 1 by rq. Derivative 1 by rq with respect to r. It will be how much? See, the second term was d by dr of this one L square by 2 mu r square. So L square by 2 mu r square. So what it will be? L square by 2 mu constant. So 1 by r square is nothing but minus r square into 2r. 1 by x derivative will be how much? 1 by x square minus 1 by x square. So this one. So L square by 2 mu into here minus 2 by r to the power 4 into r. So r, here r got cancelled. We 2 got cancelled. We found L square by mu r q. What is your initial here? Okay, L square by mu r q. Here it will be minus, is that minus? Minus will be, it will be minus. This value will be minus. Here it is minus is there. So it will be plus. Correct? Now, just multiply r dot both the side. Then here you can see mu r dot equal to minus d by dr mu plus L square by 2 mu r square. R dot is nothing but your dr by dt, right? D by dt of this can be written as d by dt of 1 by 2 mu r dot square. You check in your rough. If you are going to take the derivative of this one with respect to t, you are going to get this one. Okay. How it is? See, 1 by 2 mu r dot square d by dt. Okay, 1 by 2 is constant. Mu also is constant. So here r dot square will be 2r dot into r double dot. 2 got cancelled, and we found mu r dot r double dot, this one. And similarly these two can be here. You can see d by dr, here dr by dt. So we can write d by dt of this much minus d by dt of this much. Okay. Now that implies, see, I taken this term to left side. So collectively we can write this is minus, means it will be plus this side. So d by dt of half a mu r dot square plus L square by 2 mu square plus u equal to 0. Okay. So it will be, if it will be 0, then this will be constant. We know that some terms derivative will be 0, means that has to be constant. So half mu r dot square plus L square by 2 mu r square plus u equal to constant. Let it is your question number 6. Now we have to use L equal to mu r square theta dot in this equation number 6. Then equation number 6 will be half mu r dot square plus L, instead of L we have to write mu r square theta dot whole square by 2 mu r square plus u equal to constant. Okay. Now you can see same thing I have been written over here, same line. So now you can see half mu r dot square plus this will be half mu, 1 mu here, mu square will be got cancelled, will be mu. Here you can say r to the power 4 r square got cancelled, r square theta dot square plus u equal to constant, or it can be written as half mu r dot square plus r square theta dot square plus u equal to constant. Let it is your equation number 7. Now if we are going to search this expression is what, What is this expression? Again, I am going to be suggest that you go through your orthogonal coordinate system note, mathematical physics. You can found that velocity of the particle in spherical polar coordinate is nothing but v equal to r dot r theta dot, right? R dot radial component, r plus r theta dot is your what, transverse component or along theta component. Okay, this component we are not going to be consider, only these two component we are going to be consider, right? Same thing I have been written over here. See, v is nothing but r dot r cap. Instead of here er cap, I have written r cap plus r theta dot theta cap in polar coordinates, right? Now v dot v will be v square, will be how much, r dot square plus r square theta dot square. So here this term in your equation number 7, the term r dot square plus r square theta dot square will be what, v square. That means this represents velocity square. This is dimension of mass. So this is half m v square represents what, kinetic energy, right? Kinetic energy. So equation number 7 is nothing but this term is represents kinetic energy. This is your potential energy, always constant for a dynamics in the Newtonian mechanics that we know. So kinetic energy plus potential energy equal to constant. Let it is your equation number 8. From equation number 8, it has been concluded that the total energy, kinetic energy plus potential energy, remain constant under the motion in the central force. This is one of the another characteristics you can say, that as the plane force is confined, 3 characters we studied, remember, 3 characteristics: angular momentum has to be conserved, motion has to be sticked or confined in the plane, and aerial velocity has to be constant in case of central force motion, or the so-called characteristics. This is another, also you can say that it will be also one of the characteristics from which we can identify central force motion. That means central force also obey this one, total energy has to be conserved or constant. Now hence E equal to, that means total energy E equal to half mu r dot square plus r square theta dot square plus u equal to constant. Let it is your equation number 9. This is called second integral. See, this is the expression of the energy. So from this we can determine the what values of energy with respect to position in radial and in case of with the function of radial, with the function of theta, the E can be determined. So it is called as the second integral of motion, or you can say equation of motion. Okay. So I told that wherever you are going to be found this is the equation of motion, this is the integral of motion, means that equation or that expression represents mathematically the dynamics of the motion. That means from that equation we can found the behavior of the dynamics. Okay. Now equation number 6 can be rewritten as equation number 6. Equation number 6 is what? This one. Have this one. Okay. Now the equation number 6 can be rewritten as half mu r dot square plus L square by 2 mu r square plus ur will be constant, which is equal to E. Okay. Because whatever we have been derived up to equation number 9, that from equation number 6 only. So here this value is constant. Here 9, equation number 9 we found constant which is represents total energy. So equation number 6 also represents the total energy. Okay, this constant represents what? Total energy. Let it is your equation number 10. Here L square by 2 mu square r square is nothing but, this is important, L square by 2 mu r square centrifugal force. Remember, this is mu r is the potential energy of dynamical system. Okay, this is potential. This is also potential in the form of potential. So this is due to centrifugal force, and this is your potential energy of dynamical system. Now let this L square by 2 mu r square plus u r collectively called as u effective r. Let it is your equation number 7. Now equation number 10, instead of this 2 I can write u effective, right? So it will be E half mu r dot square plus u effective, this is the function of r. Okay, function of r. Let it is your equation number 12. Here equation number 12 is similar to the equation for the energy of the particle of the mass m constrained to move along a straight line with kinetic energy half mu r dot square and potential energy this one. Okay, you understood what this is, the constraint to move along the straight line. That means your central force acts along a radial direction, so it has to be along a straight line motion. And at the time of motion, what will be the kinetic energy? That will be the half m here m is mu, half mu r dot square, and the potential energy, effective potential energy or collectively potential energy is u f r, which is nothing but this. Now you can see this is called as the effective potential energy, and the equation number 12 involves only the radial motion. This helps us to use the energy diagram to know about the feature of the radial motion. Okay, so from the by using equation number 12, the exact dynamics of the particle we are going to be find out. Here I am going to give one example. Suppose this is your nucleus, right? This is your nucleus. I'm going to draw another figure here, it will be better. Suppose this is your nucleus. Electron is around the nucleus. One electron, suppose we are going to take hydrogen atom. One electron will be here. Now we just consider Bohr's atomic model. That means this electron is revolving with a fixed orbit. Okay, with a fixed orbits. That means, so here one can imagine that this is positive, this is electron is negative, they can be attract and they can be collapse. Okay, but according to nuclear physics, if we are going to be search inside the nucleus, this is made up of the particles which are made up of also negative charges, that you are going to study in detail in your nuclear physics. So when the electron is approaching towards the nucleus, initially it is attractive. Suppose from this distance, initially it is attractive. Okay, so attractive force up to a certain distance. Then when this electron try to come closer to nucleus, then a repulsive force acts on this electron from the nucleus due to negative charge particles present inside this nucleus. What are the negative charge particles? That you are going to study in detail in your nuclear physics. I am going to give you a simple model, or you can say dynamics of the central force. Nucleus, electron is here, it is a negative charge. So this nucleus is going to attract the electron up to a certain distance, up to this much. That's it. Suppose this is R1. Beyond that, this electron could not be moved, that it has to be collapsed to the nucleus. Whenever this electron wants to move, or going to cross this distance, or going to move towards nucleus from this beyond of this distance, means when the electron up to this much, there is attractive. If electron try to move further closer to the nucleus, then a repulsive force is going to found. Okay, so here this is the so-called minimum distance up to which we can found the attractive nature. Then beyond this distance or further closeness to the nucleus, going to get a repulsive force. And we know that if central force attractive, then it will be represented by negative, and corresponding energy also represented by negative. Force is negative, represented by negative. If repulsive, then the force will be positive and corresponding energy is going to be represented by positive. So you just keep in mind this simple dynamics, how the electrons is going to attract up to a certain distance, then repulsive with the nucleus. You just keep in your mind this model. This model is going to be help to understand the energy diagram, what we are going to discuss in our next class. Okay, so thank you so much for watching this video. Write down the note clearly and ready for the next class. Thank you.